going, we have learned Hermitian matrix. Now we learn another important matrix. Another character is called unitary matrix. Unitary matrix, again, right? If you learn quantum computing, you need to learn that two type of matrix. Hermitian, what is it again? H dagger equal to H. Okay. What is unitary matrix? I just changed the name to U. It's still a matrix. U dagger equals to U? No. This is what matrix? Hermitian, right? The inverse of the matrix. If your dagger equal to inverse, then it's a unitary. It basically says my image is equal to me if the flip the image over. So you see there's some meaning, some very important symmetry there, right? Indeed, now it depends what you mean by inverse. Of course, it may not be rotation, but this is a special matrix, okay? That is the definition, and you are done. That is the most important thing. They help you to simplify a lot of equations. But this also implies what? I can multiply U at the both sides. It's just like the subtraction, just like a regular multiplication, right? It means U times U get dagger equal to identity matrix. And if you look at quantum algorithm, you find that, hey, the first gate is U dagger, the second gate is U, then you know that the two gates cancel out. You should remove that, right? It's just like you see two NOT gates next to each other. In your logical synthesis, you got to remove that, right? Which is also equal to U dagger. But this is the special thing about the U dagger. But the most important thing is many people always forget is it preserves the inner product. It preserves the inner product of vectors. What does it mean? What is a matrix again? Step back. What is the matrix? What is a matrix, an operator in quantum computing? What's a matrix? Say again. Can you say louder? I can. It's a gate. What is a gate? Operator, what is a operator? What does it do to the state? It changed the state, right? And again, what does it mean by change in quantum computer? It rotates the vector in the hyperspace. Or you change the coordinate. So if I have two products, A and B, they have certain dot product, I rotate them together, should they still have the same dot product? They should, right, physically. It's just like the angle between the two edges of my table is 90 degrees. Now I turn the table by 90 or move it to another place. They should still have 90-degree angle, right? If not, that would be a big trouble, right? That is the same. If these two vectors has no overlap before, they're orthonormal. After you rotate it, it becomes a parallel, or they have some overlap. Then we are in trouble also, right? The basis is no longer orthonormal, right? So that is the special thing about the unitary matrix. It preserves the inner product, and that is what I'm going to show you, how it preserves the inner product. I will go to prove it, right? So assume, no, this is proof. I have two vectors, F and G. What is this? Inner product between F and G, right? It can be any vector. Okay. So I'm going to transform F to UF. Does this make sense to you? I transform F, it means that I apply the U, so it becomes a new vector, right? This is a new vector. This is new. For example, maybe I rotate it by 90 degrees. I call it F dash. If that is the case, at the same time, G is going to be UG, right? Because we are in the same world. You cannot just, like the table, you cannot just rotate this edge, not rotating another edge, right? Okay? So what is this new product, F dash G dash? What is this new product? Now, the first thing is that in order to find the inner product, I need to know the bra version, right? What is the bra version of F dash? Do you still remember the math? Transform it, at least but this is what U times F, right? How do I write it when after it's transformed? F definitely become a bra, but how about U? Instead of complex conjugate for matrix, what do we use? Do you remember? Transpose and then complex conjugate. And that is what? Adjoint. It becomes this. And you need to switch the order. Now, you might not be familiar with this. I showed you in the recording already, right? But that's okay. Just you need to record. And I missed one thing, right? I missed the dagger. So it becomes F, U, dagger. Right, this is just the equation, and I showed you earlier. Is this okay? But you should not be surprised, and you forgot, but it should not be surprising to you. You should not be surprised, because this becomes a row matrix. Then, of course, the matrix needs to be swapped, because it's from row instead of column. And always when we go to the bra space, we take the complex conjugate and transpose whenever we can. Then it's dagger. Okay? So this one is what? F, U, dagger, the whole thing, times U, G. Right? Because G dash is the new vector, it becomes UG. F dash is the new vector bra version, it becomes F, U, dagger. Make sense? Think about it. Any questions? Is that clear? Now I can always use associative rule, right? This is just F, U, dagger, U, G, right? What is U, dagger, U, G if this is a unitary transformation? Identity. And what is the effect of an identity matrix? Its effect is no effect, right? So you see that after the transformation, the inner product is not changed. That's what I want to show you. But more in this exercise, I hope that you can recall how to find the bra version of a transform vector, right? And also recognize this associative property. But most importantly, unitary matrix defined in this way preserve the inner products of every vector. So if I have a orthonormal basis, its basis vector are orthogonal to each other. After the transformation, it is still orthogonal to each other. Okay. Now I need to talk something a little bit lengthy, maybe annoying, but I will still want to go through this. It is about what is the property of the unitary matrix column and row, right? So we know that for any unitary matrix, U dagger times U equals to 1. Now I can say U is this, right? I definitely can say U is B0, 0. I use B, you can use U, whatever. B0, 1, the first 0 row, first column, row column. Memorize this row column. And then I think I should have a B0J, the J column, and then B0N minus 1. To save time, I will only do the last one, N minus 1, 0, Bn minus 1, 1, Bn minus 1, J, and then Bn minus 1, N minus 1. Is this okay? Just a matrix. Right? But I highlighted a column, which is B0J all the way to Bn minus 1J. Now, this is a good exercise. I need you to help me to create the matrix of the dagger. Okay, how do you find this matrix? What do you do? Just refract, right? The first row becomes the first column. The last row becomes the last column. Right? So I'm writing it in this way. This becomes B0, 0, B0, 1, all the way to B0J, B0N minus 1. Okay, again, I only do this. And then this one becomes Bn minus 1, 0, Bn minus 1, 1, all the way to Bn minus 1, N minus 1. It's going to be difficult for you to study. Writing is not clear. This is Bn minus 1J. Is it correct or I missed something? What do I miss? What do I miss? Yeah, there are more rows, that's right. Besides this, what do I miss? Complex conjugate, right? Transpose and complex conjugate, right? So I put a star here, star, star, star. Okay, so I complete. Now, I want you to look at this. Now, this whole thing equals to what? I. It equals to I. What is I? 1, 0, 0, 1, 1. The rest are just 0. Right? That is the meaning of I. Correct? If I call this column, I will extend a little bit further. I call this column V0, V1, Vj, Vn minus 1. Is this okay? I call this whole column V0, just a vector, right? I just group them as a vector, right? I group them. Do you see that? How do you get this element? The way you get this one is the first row times the first column. Then you get 1. First row times the second column, you get 0. So you see that you only get 1 if you have at the ith row times the ith column. But each of this row is nothing but just the transpose of the other, right? I don't do this well, but for example, this one, if I call this a cat, what is this? This is just a bra. Do you agree with what I'm saying? This row is just the brown version of this cat. Right? Because this cat is vertical, I call it Vj. I rotate it and give complex conjugate, right? And that basically is saying that for any column, V, I, Vj equals to 1, right? If what? I equal to j. Otherwise, it equals 0 if I not equal to j. And this is which symbol again? Conical delta symbol, delta ij. So what I'm showing you here is that if it is a unitary matrix, the columns themselves are orthonormal to each other. Every unitary matrix, this column is, if you do a inner product with another column, it is 0. With itself, it is 1. That is the characteristic of the unitary matrix. Okay? And this is the same for rows. Here, I'm only showing you the column. I'm saying that each column are orthonormal to each other. But same if you try to play with the rows. I will show you an example later. But is this okay? If okay, we can stop now, but I will continue. For those who want to stay, continue. I will go until 5:15, right? And in the meanwhile, if people come, we need to move to another classroom. And then the rest you can watch the video, okay? So let me continue, right? Now I'm going to show you an example of unitary transformation. Although a lot of math, but it is not difficult. So let's look at this. I have a coordinate system, which is 0, and this is 1, right? And then I have a vector, V, equals to alpha 0 plus beta 1. Okay? So that's it, right? I have a coordinate. That's it. And then have vector. Again, I try to hijack the 2D plane. It is still valid because what I'm doing is just a 2D rotation. I don't claim this is a qubit, but in some sense, they have the same result. I do a unitary transformation. Rotate it, become V dash by theta. Okay, I'm doing a transformation. Rotator, right? Just what I've been saying, right? Transformation or matrix is the rotation of the vector. Okay? Now, I can do it in this way, but in order to get the representation, it is the same as if I rotate the coordinate in another direction. Right? I have this coordinate. I have V equals to alpha 0 plus beta 1. Now, if I rotate the coordinate, becomes 1 dash by theta, 0 dash by theta in another direction. Then this V, the representation of the V in the new coordinate is the same as the new V represented in the old coordinate. Right? So that's what I want to say. Representing V in 0, 1 basis is equal to representing V dash in 0, 1 basis. Sorry for the writing, right? You see what I mean, right? This V dash representing in this coordinate is the same as representing the original V dash, but in the rotated coordinate, right? We are together. I step forward by 2 steps. It's the same as you step backward by 2 steps in terms of representation. Okay? So, then we have, let me see if I have more slide, not this one. Then we have, what is 0, right? The 0 can be represented in the new coordinate system by cosine theta 0 dash plus sine theta 1 dash. Now this one you need to try yourself if you forgot this, but this is not that difficult, right? Because when we have the 0, I'm talking about this 0, this is 0, right? This is 0. It's equal to cosine theta of 0 dash and then sine theta, not here, sorry. Looks like we have, hold on. All right, this is sine theta of 1 dash. Okay, hold on, let me see. Yeah, so hold here, then I'll try to find another room. If you cannot, then you can watch the video. Sorry? Okay, let's continue, right? So now, let me show you again why we have this. What we're saying is that this guy, for a unit vector at 0, is just equal to the 0 dash cosine theta, right? Plus plus 1 dash sine theta. Okay. Maybe. Now, so similarly, if for the 1, right, it is equal to negative sine theta times 0 dash plus cosine theta 1 dash. Okay, so this one you can try again, right? I think I drew the thing wrong. So it should be 1 cosine theta. For that one, you will have a projection to here to contribute to 1 dash, and then a 0 dash here, because this is in the negative sign, right? Because this 1 is here, right? You got some positive contribution from 1 dash and some negative contribution from 0 dash. So just take it for granted. Our goal is not to prove this. You can check this from trigonometry textbook, but I'm just showing you the transformation. So because of this, then we can say, what is V? V equals to alpha times 0, right? Let me write it again. And then beta times 1, which means it is alpha times 0 is the whole thing. Cosine theta 0 dash plus sine theta 1 dash. And then plus beta minus sine theta 0 dash plus cosine theta 1 dash. Is this okay? I just do substitution. Just take this equation for granted. You need to derive it if you forgot. Is this okay? I just do the substitution, right? So I have 0 dash and 1 dash. I can regroup that, right? V equals to alpha cosine theta minus beta sine theta, the whole thing 0 dash plus alpha sine theta plus beta cosine theta, the whole thing 1 dash. I'm just regrouping that, right? Because this 0 is here, so it's alpha cosine theta minus beta sine theta, I get 0 dash. Alpha sine theta plus beta cosine theta, 1 dash. You see that I already represent this guy in the new basis, right? So how do I write it if I want you to write in the column form? Basically, I already showed that now, maybe I should do this, right? This one is representing V in the 1 dash form. 0 dash, right? Which is which statement? I call this 1. It is this statement. Represent V in the 1 dash form, right? I'm representing this V in the new coordinate. It's the same as representing this V dash in the old coordinate. Because of this, if I call this 2, then this is 2. V dash in the old coordinate definitely is just equal to, is the same. Alpha cosine theta minus beta sine theta, but in the 0 plus alpha sine theta plus beta cosine theta in 1. Okay? Because I show you that V, the original V in the 1 dash system is this. It's the same as the new V dash in the old 0-1 system. That's why this V dash in the old 0 system should be like this, right? So then this one, if I try to write it in the matrix form, it's just alpha cosine theta minus beta sine theta, alpha sine theta plus beta cosine theta. But the most important thing is the first item referred to which basis here? 0, not 0 dash, right? The second item referred to 1. It's just a name, but you need to recognize this. So we have the V, we also have the V dash. Then I can tell you the matrix to rotate this V, the U is just equal to cosine theta negative sine theta cosine theta. This is the U for this rotation, right? How do I get it? I need to show you, but here we are going to check. I don't have enough space. Let's try to apply U to V. What is U again? Cosine theta negative sine theta cosine theta, right? What is V? V. What is V? Say again. Alpha beta. V is alpha beta. Which basis are we talking about? CO1, right? So very like what we're talking before, but now we can visualize it. Do the matrix multiplication. What do you get? You get cosine theta times, alpha cosine theta alpha cosine theta, and then minus beta sine theta, and then correct, right? Are they the same? Right. So indeed, I derived the unitary matrix. You don't need this in the exam. I don't expect you to do this, but I do want you to. I cannot say you don't need it. I don't know if I'm crazy at that time and want you to do something. I'll be reasonable, right? But the point is, I do this is pure trigonometry you learned before. You probably learned this transformation before, how to rotate a vector in a 2D plane. And that is exactly just a unitary transformation. Okay? Yeah, question?
Oh, yeah.
How do I guess? No, I don't guess. I actually look at this. I already know that u times v equal to v dash. And so I come up with this u because I see this transformation. But I just write you the answer and then I show you again my guess is correct. Yeah.
So you're just representing it in the opposite basis?
No, we are still representing in the 0, 1 basis state. I just use this one to help me to find out the U matrix easier.
Okay.
Yeah, because I can substitute this by 0 dash. Once I have 0 dash, then I get the final result already. Because the V in the new coordinates, the coefficient is equal to the new V in the old coordinate. Right? Okay, can be confusing, but I would like you to study, to replay this video, understand what's going on. Okay. How to find the transformation matrix? Just now, this one I can see it in a 2D plane. But we're talking about a space that we don't know, right? So how do we find it? This is what you need for your homework, I guess. Hopefully, this is the last thing you can finish your homework this time. That's how we do it. So if I have an O basis, right, I call it 0, 1, all the way to n minus 1. What is this? What's the dimension of this space? N. Thank you. And I want to transform the basis. It means I'm going to rotate the coordinate. Okay? Not rotate the object, rotate the coordinate. To a new basis. 0 dash, 1 dash, all the way to n minus 1 dash. Okay? How do I find the matrix? Very easy. That's how you find it. U equals to, it must be an n by n matrix, right? Because it's transformation matrix. New basis, inner products with O basis. This is what? 0th row, n minus 1 column. So each element is I, J. The ith row, jth column element is the ith new basis, jth O basis in the product. So this is, what is this? Which row is this? N minus 1. So it has to be n minus of the new basis in a product with 0 of the old basis. Up to n minus 1 of the new basis in a product of the old basis. Then we'll give you the transformation matrix. Now I would like you to go back to try this. You can find this matrix very fast. Okay? But let's try another easier one. Oh, no, actually, I'm going to try this. Yes, say again.
Did you write 0?
0 what? 0th row, yes. Yes, 0th row. Let's go back to that example. Zero. 1. One dash theta 0 dash theta. I rotate by theta, right? How do I transform the old one to the new one? U equals to 0 dash 0, 0 dash 1, 1 dash 0, 1 dash 1. Okay, write down the correct equation first, correct form first. You use this for your question 1, right? There is a way to do that. It's up to you. How to transform the Bell basis into another basis. What is 0 dash 0? What is the inner product between 0 dash 0? Huh? This unit vector and this vector. What is the inner product? Remember? In this 2D plane? Yeah, just the magnitude and cosine theta, right? Magnitude is 1. We assume, I did not say that, but we all assume 1. What is 0, 1 dash? 0 dash 1. If you do a little bit math, it is negative sine theta. Okay, negative sine theta. I already have the answer, but you see that because they're in opposite direction of the plane. What is 1 dash 0? Here, 1 dash 0. Positive sine theta, right? It's sine theta, correct. And then what is 1 dash 1? Again?
Positive
Cosine, right? Very good. This is exactly the same as the previous slide. The previous slides, you use trigonometry to do it. Okay, fine. But you cannot do it when you go to multidimensional or in the space you cannot see it, the cubic space. Here is generalized. Do the inner product. That is the transformation matrix. And if you apply this matrix to a vector, you rotate that vector. Now note that this is used to rotate a vector. Okay? Okay.